Okay, ladies and gentlemen, welcome to today's last talk of this session. The speaker is Minxin Huang from University of Science and Technology of China. He is an expert in string theory and its application in related fields. He's going to talk on PP wave holography and entropy bonds. Please join me in welcoming Professor Huang.
Good afternoon, everyone. Would like to thank the organizers for this nice conference and inviting me to give a talk. Today, my talk based mostly on these three papers and also some earlier papers that are cited in these papers. This is the outline of the talk. This talk consists of two parts. In the first part, I discuss PPWave holography, and after some introductions that I focus on the probability interpretation of PBMN two-point functions. In the second part, I discuss entropy of PBMN string and also make connections to Calabi-Yau spaces and cosmology. Okay, let me start with some general introductions. The ADS CFT correspondence is a deep idea which relates to seemingly totally different theory. And probably the most canonical example is the equivalence between type 2B string theory on ADS phi times S phi and n equals 4 SUN Sibyl-Yang-Mills theory. Although the correspondence has found flourishing applications in many topics, the precise tests of the holographic duality are mostly restricted to supersymmetry protected quantity in supergravity approximation. For example, the spectrum correlation function of BBS operator. Without alternative effective method to handle string theory in the deeply stringy regime, a common perspective is to simply take the Sibyl-Yang-Mills theory as a non-perturbative definitions of ADS string theory at any coupling and any energy scale. This is seemed to be correct unless otherwise convincingly explicitly contradicted. So usually people think of this as a correspondence of strong coupling field theory, but in this broad perspective, you can consider any coupling, weakly coupled or free gauge theory. A particularly interesting avenue for progress in the precise test of holographic correspondence in the stringy regime is to consider a panel's limit of the type 2 ADS phi times S phi background. The geometry becomes this so-called PP wave, or some people call plane wave geometry. It's first discovered by this author. It's more than 20 years ago that when I was still a PhD student, I worked on this topic. Nowadays, many people know me as a topological string person, but I work on this topic from time to time. But as I mentioned, we also made a connection to Calabi-Yau space. Calabi-Yau space probably appear in many places. It's appear everywhere. Yeah. So this is the metric that also has a maximal supersymmetry, same as ADS phi times S phi or space. There's a parameter mu measure the space-time curvature and the Moleman flux, and mu equals 0 is simply the Minkowski or flat space. The free string spectrum can be obtained in the Lycon gauge using Green-Schwarz formalism similar to flat space. So this is in contrast to ADS space where the quantizing already the free string spectrum is quite difficult. In the groundbreaking paper, Berenstein, Adesina, Nestes proposed a type of near PPS operator which correspond to type 2B closed string on the PP wave background. The free string spectrum is correctly reproduced by perturbed gauge interactions as the planar conformal dimension of this so-called BMN operators. The BMN scaling limit, here we take a large R charge that goes like the square root of n, and this is a particular nice limit that I think lies between the graviton regime, which has a small R charge, or the so-called giant graviton regime, which has the large R charge. This appears to be a promising ground for quantitative exploration of holographic duality, as a dual theory on both sides can be either free or weakly coupled. Yeah, well, as we mentioned, the free string spectrum is reproduced by weakly coupled gauge theory. Of course, there's a caveat that space-time is highly or even infinitely curved. But as we will see, this is not a big problem for string theory. Let me give some more physical motivations. Main goal of theory of quantum gravity is to understand the physics in regime beyond reach of classical gravity, for example, in highly curved space-time near the black hole singularity or Big Bang singularity. One approach is to consider ADS space, where the radius of ADS is very small. So the space-time is highly curved. There are probably some papers in the literature consider this aspect. In today's talk, I focus on this as PPWA background, which I think is simpler, easier to study than the ADS. And we will actually focus on this extreme regime where the mu goes to infinity, or the infinite curvature limit. Certainly, the effective action of classical gravity completely breaks down in this case, but this is not necessarily best situation, as we can probe the fundamental nature of space-time in a stringy regime, because this is still maximally supersymmetric background, so this has some nice property. Here, the classical geometry blows up is very singular, but as we will see, the quantum theory is completely finite and consistent, and string theory can be still weakly coupled. It's very nice. The panel's limit here provide there's a new twist holographic story. In the celebrated ADS-CFT holographic dictionary, the CFT, it's well known that the CFT lives at the boundary of ADS space and is local operator coupled to the boundary configurations of the ADS bulk field. However, although the PPWA background comes from a panel's limit of data space, the geometry is rather different. As such, it's not clear how to directly apply the ADS holographic dictionary, particularly in situation with finite string interaction. Well, as I mentioned, for free string spectrum is produced by planar conformal dimension BMN operator, so there's no problem with free string theory, but you have to be careful with string interactions. Our approach in some previous paper is to consider another corner of the parameter space, focusing on free gauge theory. In this case, as I mentioned, this become infinitely curved. The string become effectively infinitely long and tensionless, a kind of tensionless string. Some non-planar contribution was first computed by these authors. Most interestingly, since the string spectrum is completely degenerate, this tensionless string can jump from one excited state to another without energy cost through a quantum unitary transition. It turned out in this case, the string coupling constant is identified with this genus counting parameter G equals J squared over N. As I mentioned, this is a double scaling limit J and N both goes to infinity, but J square over N is a finite number. Since the full-fledged holographic dictionary is no longer available in this case, our pragmatic approach is to compute physical quantity on both sides and try to find non-trivial agreements. In this sense, a mismatch with naive expectation is not necessarily a contradiction of holographic principle. Instead, we should focus on finding aspects where the calculation do agree and try to give physical derivation or proof of such coincidence. So let's say, so besides the free string spectrum originally considered in the BMN paper, there are some more tests of the PP-way holography. So for convenience, I quote this the 3 entries of the so-called PP-way holographic dictionary. So this first entry is probably kind of obvious that it is studied immediately after the BMN paper. In this first entry, we compare the free-planar 3-point functions of BMN operator with the Green-Schwarz Lycon string field theory cubic vertex in the infinite curvature limit. So in the second entry, I propose what I call the factorization formula, where the 3 higher genus BMN correlator are related to the string loop diagram calculation by pasting together these cubic vertices without propagators. More recently, we proposed the probability interpretation of BMN 2-point functions. Yeah, so I will introduce in a moment. Sorry. Yes, that's right. So yeah, so this is just some general discussion. I will give some more details in a moment. With indirect test through this also non-negativity of BMN 2-point functions. This will be the focus of today's talk, since most interesting, and although the evidence is indirect, unlike the previous entry, you can compute both sides. In this case, you only compute one side. Okay, so now I introduce the notations. The BMN vacuum operator is simply this trace Z to the J operator. Z is, as I mentioned, is the really large R charge, and J is really large R charge. Z is a complex scalar in the n equals 4 super-Yang-Mills theory. One can then insert the therefore remaining real scalar into the traces and sum over the position with phases corresponding to string modes in 4 of the A transverse dimensions. So these are so-called BMN operators that denoted as O to the J, and there's also this integer string mode numbers, where there's in this notation that positive and negative integer represent the left and right moving stringy excited mode, where the 0 modes supergravity modes. Okay, so there's a well-known closed string level matching condition that the left moving mode and right moving mode had to match. So the sum of this integer had to be 0. This is actually quite nice that this condition is also holographically realized by this BMN operator. If this is not satisfied, then this BMN operator is automatically 0. So for one string mode, we just have a 0 mode. This is kind of rather trivial. For the excited string state has at least 2 string mode. So these BMN operators are orthogonal at the planar level. We can probably normalize them to be orthonormal at the planar level. And then at higher genus, these are proportional to G to the 2H. As I mentioned, yeah, the G is indeed the genus counting parameter. So this is an example of genus 1 non-planar diagram, but it can be drawn on chorus without crossing each other. So this is genus 1 diagram. Okay, so the BMN two-point functions are real and symmetric. This can be found by calculations, and there's also a nice formula summing over one set of string mode. This can be derived from the integral formula of the BMN two-point functions. So we can define the matrix element summing over all genus contributions with this proper normalization factor, so that it looks like probability distributions. To interpret this as a probability, they need to be non-negative. For the case of two-string mode, the negativity at any genus can be easily proven since because the two-string modes are opposite numbers because of the level matching condition. Yeah. So, this is no longer trace of Z. You insert some other operator into this trace of Z. Yeah. You mean all these are 0? Yeah, then this is normalized to be 1. Yeah. Yes, but this are not no longer BPS operators called near BPS. Yeah. Yes. We will take n go to infinity. Yeah. Okay. Okay. So yeah, let me go back to that. But in the case of four-string mode, it turns out this can be negative. There seems to be a loop forbidding this cloudiness that we cannot holographically use up four remaining string mode to occupy the four transverse directions. So the most it turns out the most interesting is the free string mode. In this case, that we are not aware of a simple proof of the non-negativity, but instead we perform the detailed calculations and explicitly verify the non-negativity up to genus 2. So now I come to the main formula of this talk. That's the what I call the third entry of PP-Way holographic dictionary. So if you just want to remember one formulas from this talk, is probably this formula that let me explain this. As the left-hand side is as I mentioned, this the properly normalized BMN two-point function, and on the right side is on the string theory side, it's a quantum unitary transition between this degenerate string where the U is an unitary operator, because this only for the case of 2 and 3 string modes. So this BMN single string from a orthonormal state of the Hilbert space. So naturally, the unitary transformation gives you a probability distribution, this norm square. Of course, the probability interpretation only requires the matrix element to be non-negative. Here, after some calculations, we make the stronger conjecture that these two-point functions with free string mode are also always non-negative separately at each genus. Okay, this seemingly simple equation has eluded research on the topic for many years because the physical picture of string dynamics in this infinitely curved background turns out to be drastically different from those familiar in flat space or ADS space with large radius. In particular, there is no finite physical process of multiple particle or string scattering to and from asymptotic region of space-time as the higher point functions always vanish in the strict n equals infinity limit. Of course, they are still very useful in some previous work, but today we only need to discuss two-point function, which is finite in this strict BMN limit. Instead, this tensionless string jump from one excited state to another state, as in a S matrix, but it's like a one-to-one S matrix, as you can see in this here. As you mentioned, this time evolution is not identified with the space-time coordinates in the Yang-Mills theories. Instead, it is emergent from this calculation of two-point function. So this is an emergent, probably an example of emergent time. One question is, you may think, why not identify the BMN two-point function with just the transition amplitude? The reason is that these two-point functions are real and symmetric. So if you believe unitarity, they cannot be a unitary matrix. So we have to identify with the norm square of this amplitude. Yeah. Okay, so I should probably skip all the details, but this is the formula with two-point function for genus 1. You can that it's indeed real symmetric. And for the case of a two-string mode, you can prove that it's apparently non-negative. This is some notation for the integral. So the case of three-string mode is more interesting. That first we consider the case of genus 1. We can discuss various cases, and you can see that proof that this is two-point function is non-negative. The case of genus 2 calculation is more complicated. There are 21 diagrams as listed here. I should probably skip the details. I'll just tell you the conclusion. That's after calculation, we check they are indeed non-negative. For example, we compute for more than 1 million random sets of mole numbers, and expect they are very non-negative. Okay, so let me summarize the first part of the talk with some discussion. The probability interpretation of two-point function implies that this genus expansion is convergent. Well, this because positive and to 1, so it's convergent. In this sense, the holographic high genus calculation are not asymptotic productive expansion as familiar in most examples of quantum theory, as discussed by Marcus in the previous talk. So if no new non-productive effect is discovered in the future, then perhaps we have found a rare example of productively complete string theory. So if our contract proposal of the entry of PPB holographic dictionary is correct, it will not only provide the first examples of systematic calculations of the norms of the higher genus critical superstring amplitude, but may also, in principle, give exact complete results for any string coupling due to the convergence of the genus expansions. There is no technical obstruction really for our calculations on the big H theory side at any genus. However, the available tools on the string theory side are very limited. Most progress in calculations of high genus critical string amplitude focus on using RNS formalism in flat space, and it's quite difficult already at genus 2. Our conjecture gives the norms of certain critical superstring amplitude, including all genus contribution. However, of course, the string amplitude are complex and consist of the norms and phase angles. As discussed in a previous paper, this unitarity can, in principle, determine a large part of the phase angle, but not completely. So our study does provide long-term motivations for future research to develop technique that can deal with string theory on highly curved background with flux and including highly excited stringy state for the purpose of direct verification of the conjecture. As I mentioned, evidence is now only indirect that we compute on one side and track the non-negativity, as well as complete determination of string amplitude, including this phase angle that we cannot completely fix at the moment. So for the moment, our verification provide indirect evidence. Now that we are more confident in the validity of the conjecture, the non-negativity for 3 string modes, and we only track it numerically, it would be better to search for a proof at genus 2 and further at any higher genus. An idea is this may be written as volume of some geometric object. It's an idea. It is widely believed that as a lesson from second string revolution, that string may not be the right fundamental degree of freedom to formulate the still mysterious M-theories instead in non-productive objects like D-planes and M-planes. On the contrary, if our conjecture is correct, it is in the very special setting with infinite space-time curvature and Lemon-Lemon flux. The tensionless closed string do provide the proper complete degree of freedom for physics at any coupling constant. So this is probably the upshot of the first part of the talk, that in other words, we conjecture that in this although highly unrealistic situation, that string theory is really a theory of just strings. Okay, so before I move on to the second part, yes, questions. Okay, then let me move on to the second part. So first, I also give some general introductions. Entropy has played a significant role in our recent development in our understanding of holography and quantum gravity. In particular, this seminal proposal of holographic entanglement entropy by Liu and Takayanagi provide significant progress in the black hole information paradox. In classical physics, the entropy is only defined up to a constant. In quantum physics, the entropy can be thought of as a logarithm of the effective dimension of the Hilbert space. So it's well known that if you have a finite dimensional Hilbert space, the maximum von Neumann entropy is just the logarithm of the dimension. But however, in our example, the Hilbert space will be infinite dimensional. In this case, the von Neumann entropy can be either finite or infinite. So we will discuss more details. So how do we define the entropy of this BMN string? So for convenience, we consider the case of two-string mode. This probability distributions provide a natural definition for this entropy. as this is similar to the general entropy in the information theory that if you have a probability distribution, then you can define such an entropy that measures some kind of information. How do we interpret this physically? Suppose we have initial BMN pure state. It's well known that a pure state has zero von Neumann entropy, and you can let your quantum state go through a unitary evolutions, and this will become a superposition of many BMN state, but it is still a pure state with zero entropy. So how can we get finite entropy? We need to ask an observer to make a measurement. So in the usual interpretation of quantum measurement, this means that you project your quantum state with respect to a orthogonal basis. And here this BMN basis is the preferred basis of the measurement. And then you have probability distributions representing the outcomes of your measurement. Now suppose the observer does not tell you the result of the measurement, then we have a mixed state with finite entropy. And the entropy is actually given by this formula. And of course, this can be also understood as an entanglement entropy between the observer and the BMN string. So this gives the physical interpretation. Okay, so now, as I mentioned, our Hilbert space is infinite dimensional. So this sum you may think may not converge. But we will derive an upper bound and show this is entropy is indeed finite. Okay. So this is a derivation for the bound for two-point function from the integral formula. You can estimate and obtain an upper bound where the strength of the BMN interaction is bounded by the inverse square law. So if the two states are far from each other, then this is becomes smaller. So summing over all genus, we have obtained a bound for this probability matrix element. Now to estimate the entropy, we choose such an integer n0 and divided the sum into 3 parts. And using this estimate of the matrix element, we find an upper bound for the entropy. This n0 can be this arbitrary number satisfying these conditions. Now we see that this sum is convergent. So indeed, the entropy is finite for a finite coupling. It's interesting to consider the strong coupling limit. As we mentioned, this string perturbation series is convergent, so we can extrapolate to strong coupling. In this case, we choose the scaling of this integer as in 3 to the 2 plus epsilon. So we find the upper bound for the entropy in the strong coupling limit that goes like the log of the coupling. And this similarly can be also applied to the case of free string mode, and we get a similar upper bound. Okay, so this as an example, we plot this entropy and its upper bound in the range of G from 0 to 10. And previously, we had calculated this BMN two-point function up to genus 2. So with this data, that this provide a good approximation for the entropy in this range. This appear to be a monotonically increasing function. Is intuitively easy to understand because as G increase, the probability will become more evenly distributed. So the entropy become bigger, but it seems difficult to give a rigorous proof. Okay, so in the next step, we compare to this switch to the thermal entropy of quantum system compared to the thermal mixed state in a quantum system can be obtained as a reduced state tracing over one party in a thermal field double state. This is a pure state entangled between two similar systems. The von Neumann entropy of the thermal state is the entanglement entropy of this thermal field double state. So denotes this lambdas, the eigenvalues of an Hamiltonian. For a thermal state, the probability is given by this Boltzmann distribution. So we can compute the entropy. And it's well known that this can be written in terms of the partition function. For example, for the just as an exercise, that for the case of harmonic oscillator, this examples are quite simple, that we can compute the partition functions and entropy exactly. This is given by this formula, and we can take the high temperature limit and show the asymptotic behavior of the entropy goes like the log of the temperature. So more generally, in more general system, we cannot solve the partition function exactly, but we can write it as an integral. We will use this number of state. This is like a step function if you have a discrete spectrum. So the sum of in this partition function can be written in as an integral. So we consider another class of system known as Klabiau quantum mechanics. This is a quantum system derived from toric Klabiau geometries, where the Hamiltonians are exponential functions of the position and momentum operators. So for example, these are the two well-known models. So in some previous work, the exact quantizations can be written in terms of the defined topological string partition functions known as this TSST correspondence. So I think Marcus gave this name. You can ask him to, if you want to know more about this. So today we'll use some nice mathematical results on the asymptotics of the energy eigenvalue proven by these authors. They prove that the number of states that are just defined here, that goes like this asymptotic behavior goes like log lambda squared. So in the high temperature limit, the partition function can be written as this integral. This actually can be written in terms of a special function known as the major G function, and we can derive its asymptotic behavior. So we find the asymptotic behavior of the entropy for the Calabi-Yau quantum system, that it turns out this entropy grows much slower than conventional model because it's a double log, and for harmonic oscillator, it's a log of temperature. And we can consider whether it's possible to have a finite upper bound for entropy in the infinite temperature limit for some quantum system. So I should probably speed up, but the upshot is that for under some reasonable assumption that, for example, the Hilbert space is infinite dimensional, the partition function is well-defined for any temperature, then we can easily calculate that, so that the entropy is unbounded in this case as the temperature goes to infinity. Okay, so finally we come to the cosmological applications. Folklore of quantum gravity is the finiteness of entropy in contrast to the divergence in genetic calculations in quantum field theory. Of course, the dimension of Hilbert space is infinite in perturbative string theory, but this is not necessarily in conflict with the folklore. So people have considered this question in the 1970s. For example, see this review paper that in infinite dimensional Hilbert space, the density matrix with finite entropy is measured zero set in the usual topology. So basically, if we allow to consider arbitrary matrix generically, it seems that the entropy is infinite. But however, as in reasonable physical situation, as we have seen in our previous example, the entropy is always finite, although the Hilbert space is infinite dimensional. I should mention that here we consider this a discrete spectrum, meaning that we have a countable basis for the Hilbert space. Of course, in physics, we usually consider continuous spectrum, for example, the energy and momentum eigenstate, but however, to my knowledge, the mathematicians don't call this Hilbert space. This is not really well-defined. There's no well-defined phenomenon entropy. So you can say that I consider a kind of a bounded system with a discrete spectrum. There's no asymptotic state with continuous quantum number. Of course, if you know something about Neumann algebra, there's three types of Neumann algebra, but for the second and third type, is entropy is well-defined or only defined up to a constant. So here I can consider a pretty simple setting, just the type 1 for Neumann algebra. Okay, so this is some examples. So if we consider a probability distribution that scales like a power law, then in this case that the Neumann entropy is also finite. So how do we have infinite entropy? This is example where you can have infinite entropy that have a more contrived probability distribution, goes like 1 over n times log n to the alpha. So in this range, you can have a probability distribution with infinite entropy. But as you see, that this looks kind of contrived, although in a mathematical sense, maybe this is very generic, but I don't know any physical situation you can have such infinite entropy. In the quantum model, we study the entropy is finite at the finite temperature, but although it it's unbounded, it tends to infinity in the infinite temperature limit. So we can ask the question that whether you can have a finite maximal entropy in a similar natural limit. In other situations, this is come to the motivations come from cosmology. An important source of this motivation comes from the finite cosmological event horizon of the Sitter space. It is well known that our universe is dominated by this so-called dark energy, which caused the accelerated expansion of the universe. So you have a cosmological event horizon. In the 1970s, Gibbons and Hawking proposed that similar to the black hole entropy, then this you can apply this same argument to the whole universe, that this cosmological horizon also represent a kind of entropy. So the nature of this dark energy is not entirely clear at this moment, but one possibility is that it's a positive cosmological constant. This is indeed the assumption of the so-called standard model of cosmology, known as the lambda CDM model. I think for the moment that I'm not familiar with some recent experiment, but for the moment, this standard model of cosmology still fits quite well with the data. So if it's not a cosmological constant, it probably cannot deviate too much. So for the purpose of this talk, let me assume dark energy is just a cosmological constant. So let's say consider a four-dimensional de Sitter space with a positive cosmological constant. You can write down the metric and compute the horizon radius and vacuum energy. And here I have a convention that this cosmological constant has a mass dimension 2. So the astrophysical observation suggests that the cosmological constant is very small. It's 10 to the minus 122 in the unit of Planck mass. So this is a famous cosmological constant problem. Why it's so small? Because this is a big problem if you consider the vacuum energy in quantum field theory is naturally it should be the order of Planck mass, but it turns out to be very small. But from another perspective, we can rephrase the problem is why the entropy of our universe is so big. The idea is if you find some natural way to compute the entropy of our universe, then you can have also an estimate of the cosmological constant. So let me explain a little more about the entropy of our universe. Our universe is not just empty the Sitter space. It has many stuff, for example, the dark matter and all these things. In astrophysics, people have estimated the entropy of various components of our universe. For example, see the recent survey in this paper. In generic scenario, the dominant contributions to entropy inside the cosmological horizon comes from this supermassive black holes at the center of galaxies. For example, one of these black holes may contribute a huge entropy of 10 to the 90. Well, this is probably not too surprising because a black hole is a kind of a maximal entropy object. So for example, if you have a star that collapses into a black hole, this entropy could increase by more than 10 order of magnitude. So it's not surprising it's dominated by black hole. And I also mentioned that although the dark matter contribute about 25% to the energy of our universe, but its contribution to entropy is quite small, because dark matter is too weakly interacting and too cold. So by some estimate, probably the entropy of the dark matter of entire universe is probably only comparable to one of this supermassive black hole. Okay, so by some estimate, there may be a trillion of this supermassive black hole in our universe. So you can count the numbers that this total entropy is still negligible compared to the Gibbons-Hawking entropy of the cosmological horizon, which is 10 to the 122. And this is usually understood as regarded as coming from degree of freedom beyond the horizon. So the contribution to entropy mostly come from the stuff that we cannot see. Okay, so the entropy of our universe is finite, although it's very big. It's indeed a good approximation that this gives the entropy of the universe. And probably will not increase much in the far future. Well, the future is probably not entirely certain, but at least in some likely scenario that we assume that the standard model of cosmology is correct, that assuming dark energy is a cosmological constant, and this cosmological constant is really a constant that does not change in the far future. In this scenario, that for example, that our universe in the far future will be completely dominated by the dark energy, that or the galaxy will move beyond the cosmological horizon. And the cosmological horizon area will increase a little bit, but not too much, as still the same order, because currently our universe is already 70% dominated by dark energy. So what does this mean? One possibility is probably maybe for some unknown reason, there's a universal finite upper bound for entropy in consistent theory of gravity. This bound just bounded the entropy of our universe. And you may say, well, the Hilbert space can be infinite dimensional. But although this can be infinite dimensional, we are not aware of robust example where this entropy can become arbitrarily large, even much larger than the entropy of our universe in a reasonable physical process, taking into account the full effects of quantum gravity. Well, if you think you can construct a example, you can tell me later, but the difficulty here is I require you to consider the full effect of quantum gravity. If you don't consider gravity or just classical or semi-classical gravity, this probably does not count as an example. Okay. Okay, so you may think you cannot test this idea because in general, we don't have a full theory of quantum gravity, but in this very special example that I conjecture, we have a full theory of gravity in terms of this described by this BMN string. So they provide such a test. For the BMN string, was found that, as I mentioned earlier, that at the finite coupling, the entropy is indeed also finite. While it is naively expected as G goes to infinity, the probability will be evenly distributed among the infinite dimensional Hilbert space. So the entropy should likely goes to infinity. If this is in this scenario, then I would agree my speculation is wrong. There's no upper bound for the entropy of for no bound for entropy in quantum gravity. But however, the second scenario would be more interesting, that there would be in fact, a pleasant surprise that if it turns out this entropy of BMN string does have a finite upper bound as G goes to infinity. Such a bound may be related to the entropy of our current universe. So as you mentioned, if this bound does exist, I think it will not be, it is certainly will be bigger than the entropy of our universe, but it should not be too much bigger, because if you consider entropy always increase, so if our universe is a typical universe, then it should not have entropy too much smaller than this theoretical upper bound. Thus, this could provide a natural estimate of the cosmological constant. An encouraging hint is that for Calabi-Yau model, this is like a kind of a toy model of quantum gravity topological string. This entropy does grow much slower than conventional model. So there are many questions in this talk. In fact, this work may produce more questions than answers. However, I think this last question here to happen to be what I think probably the most interesting question at the moment. So I just conclude with this question that it would be interesting to settle this issue, whether the entropy of BMN string is bounded or unbounded. So this is the end of my talk. Thank you.
Okay, thanks for the very nice talk. Is there any questions?
I just have a question. So in this tensionless string ADS5, I guess there's some reference like by Hong Liu said there's like a transition, Hagedorn transition. They said that in the new phase should be described by some bizarre theory. I wonder whether tell that from your
yeah, it's also very interesting to consider ADS space. Here I focus on this PPY background. Actually, this I didn't mention that because the strings are infinitely long. So if you know the hexagon temperature is inverse proportional to the string length. So in this case, actually you have the hexagon temperature is 0 because it's infinitely degenerate spectrum. So yeah, it's not clear how do I study the thermodynamics in this case, but I can define the entropy that from this probability distribution, but it's not clear to me whether the temperature is you can increase temperature to a finite value because the hexagon temperature is actually 0. Yeah. Yeah. So I don't know where there's phase transition in this case.
Yes. Maybe I'm a bit more familiar with BFSS, but I think the intuition is kind of similar. So there is a regime where the temperature is low enough for a gravity dual to be computed in supergravity, in 10-dimensional supergravity. In this case, you're taking mu to infinity.
Yeah.
So you can say that the ratio between the temperature, the effective temperature, and mu is small. And then that you expect to have some kind of gravitational description, which which can be computed from Monte Carlo and things that people have looked into, right? And I think those tools should somehow match what you are computing. Or are you working strictly at 0 temperature?
Well, I think in this case, this is probably a stringy regime that the gravity is not valid. Yeah, let me go back to the this previous case. Yeah, so yeah, so probably classical gravity is not valid here, but what I consider is that this is a kind of a string theory. This Yang-Mills theory still describe a kind of a string theory, and my assumption is that this unitarity should be still valid even in this case. That's why you can write this formula.
But even at 0 temperature, I think there are more states that look like a trace of set to a finite power.
Well, in this case, actually, we are taking a kind of a double scaling limit that is not a finite power. It's a J.
Yeah, I understand. So these are J goes to infinity here, right?
That's right.
Yeah, but in principle, there would be like a trace of set to the J, and those are the ones that are related to the giant graviton.
Yeah, so this is a scaling limit that between the graviton and giant graviton. Yeah, so in giant graviton, you have J goes like order of n, but it is probably no longer described by this trace operator, but described by determinant operator, yeah, or sure operators. But in this regime, that this stray goes like square root, and this trace is still a good description of this string. Yeah.
Okay. Is there any other questions or comments? Okay, let's thank the speaker again.